Assumption of continuous variable quantum distribution. The floor is yours.
Thanks. Hi everyone. So yes, I'm Yoann Piétri. I'm an experimentalist from Sorbonne University in Paris. It's a real pleasure to be here today. Big shout out to the organizers for this really nice workshop. And I think the next slide will not teach you anything because we all know about quantum technologies, but still. So usually we speak of quantum technologies. We have like the enabling technologies, also all the theory and the subsystems, and then we usually have four pillars, which are communication, computing, simulation, and metrology, sensing, and imaging. And apart from Carol's talk and also the talk from this morning on signaling, all talk were on computing, simulation, and a bit of metrology also with quantum clocks. And I'm going to be the third talk on communication. So, and what I'm going to do also to talk, which will be I think the first one, is about QKD. And for just everyone here to agree on what it is, you take two trusted users that we usually refer to as Alice and Bob. They are provided with a public quantum channel where you can send quantum states. So in quantum communication, we use a photon because it's the only one that flies, so we use it. So it's optical fibers. And you have an authenticated classical channel, also public. And provided these two things, Alice and Bob, they can exchange a random secret string, even when the eavesdropper, Eve, has unlimited power, or at least bounded by the laws of quantum physics. Right? So she could have a perfect quantum memory, perfect quantum computer, and everything, and you will still be able to exchange a secret key. And before I enter in the results, maybe the first question is why? Why do we study this energetic consumption of QKD, but also overall? And I think there is two main reasons. The first one is that it could be that the quantum implementation offers a genuine advantage in terms of energetics. Right? This could be another form of quantum advantage, not only time. This was also what was presented a bit in the boson sampling talk from Candela, is like you could have actually an energetic advantage. And the second reason is also we have many implementation possible today, especially in computing where you have a lot of qubit possibilities, but also in QKD. And you want to select the one or the ones that would be more efficient for wider scale adoption. And I just want to comment a bit on point one here for QKD because I think it's very important. It's not really related to the result, but I think it's really important. It's like, how do we do this for QKD? Because if you take, for instance, quantum computing, you could take a specific task, for instance, the task of factorizing large integers. In the quantum world, we have Shor's algorithm, right? And in the classical world, we have the general number field sieve algorithm. You look at both of them, you look at how much time they will take, how much energy they will take, and you can compare them. And this has only one answer, right? I mean, well, it could have several answers, but all of them are wrong except one when you factor integers, so you could actually compare them. In QKD, however, what do you compare QKD with? So this is me working in the lab. I put this picture before I knew it was going to be on YouTube, but anyway, let's roll with it. And what do you compare it to? Because classical algorithms that exchange keys, they do not provide the same security. Maybe you could argue we can go back in the time before we actually did this with the uncurved briefcases. What do we compare to? And actually, I think comparing QKD to post-quantum cryptography in terms of energy is really important, but I don't think we have the tools yet to do it. Also, just for the anecdote, last year I was in Padua. We were doing an experiment with people from the Technical University of Denmark, DTU, and they went back by plane with 24 terabytes of data from the experiment. Actually, 1,000 kilometer 2 hours plane, if you look at the rate, it's not that bad. And you know, like if you put just random key, you actually have secret key distribution. The rate is not that bad. If you do it in bike, the energy efficiency may be really good also. So of course, it's a very good question. How do we compare QKD with classical methods? Anyway, for now, let's try to compare QKD protocols between each other. This is already a good thing. And I want to mention that there was a previous study on this that we did with Raja and Fede and other co-authors, where we took an hardware-driven attitude, where we look at basically, okay, what is the consumption of everything in the QKD setups? And from there, we're able to compare several CV-QKD and DV-QKD protocols. And I was thinking, okay, now, it's really dependent on the hardware we used, right? If we change laser, we'll get other numbers. So I think, okay, how can we make a bit less hardware-driven? And this is what I was starting playing with, and I actually found a bit of counterintuitive results, which I found interesting, and then this is why I'm here today to present them. So anyway, let's dive in CV-QKD. So what is CV-QKD? Basically, the idea is like Alice, she's going to prepare covariant states. So imagine you have one of these 4 covariant states. At each round, she chooses one randomly, and then she sends them to Bob. What will happen in the quantum channel? There is 2 things. First of all, you will lose photons, so they will get closer to the region. It's not represented. And the second thing, you will get an additional noise beyond the quantum minimal noise of 1 on each quadrature when you normalize with alpha equal 2. And this noise is called the excess noise. And what you can do with this is to say, OK, now let's say we assume that all of this noise is coming from the eavesdropper. You can bound the amount of information that the eavesdropper has gained, whatever was our measurement. Then you take out this information from the mutual information, and you obtain what is called the secret fraction. It's how many bits you can extract, secret bits you can extract per state that you are sending. And I will show you a bit after on what parameters depend on how you compute it. And this is what you do if you want to implement them in practice. You take a laser, you modulate them with what is called an IQ modulator, and then you are going to basically reduce the state to the photon number you want. So usually there is an optimal number of photons per state. I will also speak of this a bit later. Then it travels toward Bob's. Ignore a bit the beginning, it's not very important. And then what you do is like you mix your state with another local oscillator, and you send them to 2 photodiodes, and you detect the difference. And this difference is proportional to the quadrature. And then you have a lot of post-processing to do, and also error correction, privacy amplification, which actually I want to mention were not taken into account in the study I was mentioning before. And then you have your final key, right? OK, so this is what I actually do when I want to implement CV-QKD. And I just want to mention a bit here a difference with DV and with also a lot of, I think we heard when speaking of photonic technologies is about the detection. So here is what is called a current detector or homodynamic detector or balance detector. It has several names. One of its main advantages, it works at room temperature. And actually, the rate is also far higher. Efficiencies are roughly similar. The price is very different, but especially what I want to show is like the difference in power consumption is like by a 3 order of magnitude, basically. So these detectors are very interesting. They might be a bit less interesting for computing. I don't want to enter too much in the detail, but for QKD, they are very interesting. And this is one of the SNSPDs we have in the lab, and this small part is a balance detector with the beam splitter that you have here. So of course, they are also very different in size. OK, so now let's go to actually energy efficiency. So we define, as I think it was several times defined before, the energy efficiency, which is a ratio of the secret key rate to the power consumption, which gives you a number in bit per joule. And it basically represents the cost of running network. So it does not have any initialization cost. And if you look at the inverse, you have the price per secret bit, basically. How much energy you need to input to have 1 secret bit in your secret key. And actually, all my plots will be presented as the invert of the energy efficiency, so the cost, and the lower the better. OK, so let's dive into the detail. You have your key rate here. So we have two parameters to estimate, key and P. Key rate is simply the secret fraction times the repetition rate. And it depends on a few parameters. You have here the reconciliation efficiency, mutual information, and all over bound that was mentioned before. And this depends on 5 parameters, these 2. So the average photon number that Alice is sending, the channel parameters, T and C, which I want here to mention something with respect to the MNL metric that was also presented several times. In QKD, your assumption is like the noise is actually imposed by the eavesdropper. In practice, it's not. There is some noise that is actually coming from you, but this is a different paradigm, right? The noise is imposed by the eavesdropper, so in theory, you cannot control it. And then you have the detector parameters, which are so this is the losses and the noise of the channel. This is the losses and the noise of the detector that usually considered trusted. And for the people that love all the numbers, they are all here. I just want to mention 2 things. First of all, I will consider 2 detectors, one that will be perfect and one that will be realistic. A few words on this. A fixed amount of noise here. And I will optimize over the number of photons that is sent by Alice, and I will explain there is a small twist in that. For the realistic detector, I take these detectors that I've been using. Anyway, it's not very important, 72% efficiency. One thing that is important is like the amount of noise that you have is normalized in what we call shot noise units. And basically, it's just dividing this electronic noise by the shot noise, but the shot noise is linearly dependent on the number of photons you will input into the local oscillator. So this will also play a role. Okay, and for the power consumption, I'm going to take really like the minimal thing you need to do, and I'm going to look at the optical state that we are going to send. So the optical state that Alice is sending and the optical state Bob is using to make the interference and to make the measurement, this ignores a lot of other costs that you have, and also I will make the assumption that you don't recover anything from these optical states, right? So any energy that we are putting here is lost. And so what happens is like we are going to put it in two sides, the emitter power and receiver power, which I'm going to explain now. So for the emitter, we take the current state, we take the average number of photons, and roughly just this average number of photons times the energy of the photon, and you multiply it by the repetition rate to get the power of the emitter. For the power of the receiver, it's the same, no? Because you also need to create one current state per received state from Alice. So it's the same formula, but now you replace n with the n of the local oscillator. And then you have a question, is how do we estimate NLO? And there is two things. First of all, there is the one in the realistic detectors that will depend also on the electronic noise. But also, you need to have a valid detection. And if you look at the theory, you actually have two conditions to have a valid homodynamic detection, which are those. And so basically, you need to be far, far greater than 1 in the number of photons in the effective number of photons of the local oscillator, and far, far greater than the number of photons that you receive. This is the number of photons that you receive on average, and this is the effective number of photons, so it depends on the efficiency of the local of the receiver. And basically, you get this condition. That is that your number of photons must be far, far greater than the maximum between the inverse efficiency and the number of photons that you receive on the receiver. We'll take two cases. One will actually optimize in the max, and one will take just a constant value that is far, far greater than both of these values. Because, of course, this depends on the transmittance. So this is what we refer to as the optimized case and a constant case. So now we have all the parameters that we need to estimate the energy efficiency. You will notice something that is interesting is like this doesn't depend on RS. So the repetition rate, because it cancels out, it's almost true because VL depends on RS. So if VL is not 0, then you will have dependence on LS inside the formula of the key rate. Also in practice, of course, the higher you go in repetition rate, the more computing power you will need also. The second thing is we have an unknown parameter that is the number of photons that we need to optimize. And there is two ways to optimize it. Either you take the one that maximizes the key rate, or you take the one that minimizes the energy cost. And I will take both this case, and we'll see what it gives, right? Okay, so now that we have all the things, we can go into the results. So first thing I did, plot against the attenuation, and this is what you get. So in orange, you have the one where we take a constant LO power, and the one in blue, you do the optimization. And the dashed line is where you optimize over the energy efficiency, and the one in full is where you optimize over the secret key rate. So we see that they have almost the same tendency, except for this part here. So actually, this part is where you have a change between the inverse efficiency and Tn. And if you optimize the SQRL, actually, at this point, you can just send a lot of photons, because if you are very close to 1 in efficiency, Alice can send many, many photons, and then you need to have the local oscillator follow this. So actually, this diverges when you reach 0. But for most of parts, so once you pass this regime, optimizing over the secret key rate and optimizing over the energy efficiency is the same, which was not necessarily expected. So this is the first thing. And for fun, I also plotted the result we obtained with Raja and Fede in the previous paper. And of course, sorry for this, I had to change the scale because it goes very, very far up. And we have a lot of, like more than 10 orders of magnitude above. But we have the same tendency. And it makes sense because at some point, basically, your power consumption gets constant, even in especially in the high losses case, because your number of optimal photons actually gets to a constant value. And so it's just the tendency of the key rate. I want to mention two things. First of all, if you optimize your hardware, this can go down. But also, if you consider all the costs, then the optical cost, this will also go up. So yes. And another thing I want to mention also here, you make kind of the assumption that you can create the state that you want to send only by placing it in the phase space. What we do in practice is we generate a large state far away from the zero, we modulate it, and then we bring it back by a lot of losses. So of course, this is not very an efficient process, and this also explains why you have a big difference. But then the interesting results comes when you consider a realistic detector. So now VL is not going to be 0 anymore. It takes the values that I was giving you before. Yes, sorry, this is really fast. I did it also for finite size. You get the result that you expect for finite size. What you get is that you can make now, at a fixed distance, you can look at energy efficiency, inverse of energy efficiency with respect to the number of photons in the local oscillator. So you have two competing effects when you increase the local oscillator. First of all, VL decreases because it is a normalized electronic noise, and so the key rate increases. But you also need to increase the power of the receiver because you are sending more powerful states, and so the power increases. And what you would find in the energy cost is like this first decreases slightly, but really slightly, and then it increases when you reach high power. So you see that the power of the local oscillator at the rate I was considering is between 1 microwatt and 10 milliwatt. This here is usually what we use in CV-QKD. But one very interesting thing is like in red you have the key rate. And so in blue, the energy cost varies from 10 to the minus 10 to 10 to the minus 9, so 1 order of magnitude. The key rate on the other side varies by 5 order of magnitude. So at the cost of 1 order of magnitude more in the energetic cost, you get 5 order of magnitude in the key rate. I would say this is good news because people, when they will use their CV-QKD system, they will not operate at the minimum energy, they will operate at the fastest key rate. But actually, it might not be so actually detrimental for the energy efficiency. And then what I wanted to do was interesting is to look at this optimal point and to plot actually the optimal point in function of the distance. This is what is in the next slide. So I'm sorry about this, is the limit of the optimization bound. It's not very important, it just diverges at low distance for the same reason as before. And what you will see is like this optimal point gets to an average value. I'm not sure about the noisy things. I believe like it's very flat and it's kind of floating point errors in the computation of the key rate. But what is really important is like your optimal VL in red here is around 3,500 to 500,000 SNUs. 5,500 SNUs. If you don't know CV-QKD, you might say, oh, okay, it's fine. Usually we operate at 0.1. So it's very different. So the optimal energy efficiency is very different from the actual points we're using in CV-QKD. But as I said before, you are very far, but you will have also a much better key rate by doing so. Okay, so here I arrive at the conclusion. I just want to do a bit of summary. So we have a kind of a lower bound on energy of CV-QKD considering the optical operations with several optimization, but actually the good news is like it doesn't seem to depend if you optimize the energy efficiency or the key rate for most of the things. And we have counterintuitive results when we consider realistic detectors with respect to what we do in practice. And yeah, so a few perspectives on this. You could try to also input have the energy efficiency in optical generation, which I already said was quite bad because of this reduction. Try the contribution of the classical post-processing and the classical cost and all the cost. But I think also what is important is like more generally in quantum communications to look at also more complex protocols in network, but especially at this, which is the classical methods in QKD, comparing them, which I think is highly non-trivial, and also all the classical costs that in the initial study with Raja and Fede, we found that it actually dominates. So probably at the end, it will be the classical cost that dominates, and I think it's really important to look in it. And on this, I would like to thank you for your attention, and I would be happy to take any question.
Thank you for the very nice talk. We have some questions here.
Thanks a lot. How do we have a vision of the comparison of the energy needed for establishing the QKD pairing versus the cost of the transmission of the real data through the classical link? Because at the end, QKD is establishing the communication between 2 points, but you still need then what's the order of magnitude comparison between both?
So you mean between the quantum
Between the
data
transfer of the data and the cost of the transfer of the data versus the cost of the transfer of the key through the QKD metrics.
Okay, so at the end, probably when you will have to transfer the classical data, you will also use photonic links, but of course you will need error correction on this. So you will also need to look at how many classical data you need and what is the cost of sending this. I believe that at the end, in the QKD protocols, it will not be this that, especially in CV-QKDs, that will dominate. It will be the classical post-processing, like error correction on the quantum data itself, because you also need the reconciliation step, and this reconciliation step in CV-QKD is quite heavy, and I think this will be the dominating point.
Thank you for the talk. It's just a general curiosity about communication. So I understand that conceptually it's better than the classical way we do things. But for instance, if we have access to if we have access to post-quantum cryptography outside of a conceptual advantage in practice, is it? I mean, yeah. What does it give in practice?
Yeah. So basically the question is about what is the actual in practice advantage of QKD, and I think this is a really good question. I don't think we have a very good answer yet. So of course, what is my intuition on this is like the complexity to implement QKD and the energetic cost will be way higher. So of course, if you look only at the energy but not at security points, you would say, but let's use PQC. And on the other side, because one is information theoretic security and the other one is computational security, if you look only at security, you would say let's use QKD. But then the question is, okay, like this is a very black and white comparison. So you have many questions. For instance, what is the actual security also when you consider side channel attacks? What is the security if you actually do PQC and QKD at the same time? And you have a lot of questions that are not answered. And I think this is what is actually needed for doing the comparison I was talking about to compare QKD and PQC.
Thank you.
Okay, so thank you very much. This is all for questions.